Hi, I'm Yang Hu, presented the Self-Supervised Direct Learned Battery Descriptor. This is done by Bing, Yang, Bo, Xiuni, Weishen, and Xinbo. In this work, we focus on the end-to-end battery descriptor. And first, let's give an overview of this paper. We present a plug-and-play layer, battery transformation layer to solve the problem. Batterization process is not compatible with stochastic gradient optimization because it's not differentiable. We introduce the contrastive learning into the battery descriptor domain by BTL and propose direct learned battery descriptor as a framework. From this page, let's explain our paper in more detail, compared to the common real-valued representation. Like the popular approach, contrastive learning, battery descriptor can reduce memory consumption and computational complexity. But there's a problem that the batterization is not differentiable. To solve this problem, we present a plug-in double battery transformation layer, simply named BTL. Battery transformation layer can unlock the learning capability of neural networks for battery vector, rather than estimating gradient precisely. Gradient estimation has a wider range of applications, but it's also more difficult to study. The existing gradient estimation methods don't work well in practice. Utilizing the battery transformation layer, we introduce the contrastive learning into the battery descriptor domain and propose direct learned battery descriptor as a framework for battery descriptor. Batterization is usually performed as a post-processing. This will inevitably result in a gap between real and battery values. Although many novel and useful approaches narrow the gap, there are still issues such as no generality, additional hyperparameters, or other something. Therefore, we try to explore towards a generic pipeline for battery descriptor, which can help transferring the method for real-valued descriptor into the battery one with no bells and whistles. To summarize our work, we make the following three contributions. The first one, we propose the battery transformation layer. It's a model-agnostic plug-in layer, yielding direct learned battery descriptors, which fully utilize the advances of deep learning. The second, we propose the self-supervised learning framework to directly learn a battery descriptor. It can be deployed for various tasks, such as image retrieval, patch matching, and image classification. And the last one, an ultra-wide temperature-scaled cross-entropy loss is proposed for DLBD, enabling more diverse distributions in representation space to satisfy the various computer vision tasks. Focus on this figure. It shows the structure for our models. We try to transfer the recently common real-valued representation learning method, contrastive learning, into the battery one by plugging a layer, achieving a direct learned battery descriptor fully optimized by stochastic gradient optimizer. The end-to-end nature of networks for battery descriptor bridges the gap between real and battery values. We hope the mentioned plug-and-play layer to have some properties for enabling the backpropagation of the end-to-end model for battery descriptor. The model is optimized by any one stochastic gradient optimizer, and these properties are firstly, the plugin can normalize real-valued input to keep the gradients powerful for optimization, as shown in figure. This is a function of adjusting gradient magnitude. Secondly, to ensure that the real value is the same sign as the transferred battery value. This is corresponding to the operation of adjust gradient set. For connected layer is for the last property. The dimension of real valued vector is same as that of battery vector. Also, we introduce an additional century procession to avoid the model degradation. The last work focused on the loss function. That's because the contractive loss doesn't work well with some benchmark tasks for battery descriptor. The proposed function is named ultra-wide temperature scaled cross-entropy loss. The temperature hyperparameter tau was changed from exponential factor to multiple factor. This can enable more diverse distributions in representation space to satisfy various computer vision tasks. From now, there are some experiments. The experiment this page is to show the comparison between different generic batterization processes. The results in the table shows our proposed battery transformation layer helps model get the best performance. When we transfer the contrastive learning into the battery descriptor domain by plugging battery transformation layer, even the 16-bit battery descriptor incurs neat performance loss. This is the most important contribution in our paper. Also, we give a ablation study there to show the effectiveness of each element. In summary, we show the novel way to deal with non-differentiable problem for optimization. BTL as a plug-and-play layer can be used to transfer the approaches for real valued descriptor into the battery descriptor domain and propose a generic end-to-end framework for battery descriptor. For future research, we focus on the generalization of methods for transferring real value to discrete value. The video is over. Thanks for watching.